Hello everyone, I am Mudit Saxena, working as an assistant professor in the Department of Electronics and Communication Engineering, ABES Engineering College, Ghaziabad. Today I am going to deliver a lecture on the topic parallel biased clipper. So these are the contents of my presentation. So let's start with the very basic, what exactly the clippers are. Clipper is one of the most important application of a PN junction diode. Clippers are basically used to clip off either complete positive half cycle, complete negative half cycle, or a portion of it. Or we can also say it limits either the positive or negative amplitude of the given voltage. The basic clipping circuits employ diode and a resistor. While analyzing the numericals based on clippers, first we need to keep in our mind, which is the important point, when the diode is forward biased, it will act as a closed switch, and when the diode is reverse biased, it will act as an open switch. Also, different clipping levels can be obtained by varying the amount of battery voltage or by interchanging the position of diode and resistors. So by these two ways, we can achieve different levels of clipping. Now let's come to the classification of clippers. Clippers are broadly classified into two categories, unbiased clipper and biased clipper. Unbiased clippers are those wherein only input voltage is given. No external battery is connected in case of unbiased clippers. But in case of biased clipper, apart from the input voltage, external battery is applied. So those circuits are known as biased clipper. Unbiased clippers are again broadly classified into two categories, series and parallel. Similarly, biased clippers are of two types, series and parallel. Now here the question arises, how do we come to know whether the given circuit is of series or parallel clipper? So, if, as I have told you just now, diode and resistance are the most important circuits or components for clipping circuits. So if diode and resistance both are connected in series, that will be a series clipper. And if diode and resistance both are connected in parallel, that will be a parallel clipper. So by seeing the direction or direction of diode and resistor, we can classify whether it is a series clipper or parallel clipper. Now let's do some problem based on the parallel clipper, because in this lecture we are going to discuss the biased parallel clipper. So this is the first problem which is based on biased parallel clipper. So in the first numerical we have taken the ideal diode. So here you can see the diode which I have used is ideal. So here we can see the input is sinusoidal, which is having magnitude of 10 volts. So first of all, we will draw the input waveform. So here you can see I have drawn the input waveform, which is having magnitude of plus 10 volts and minus 10 volts. Now let's start with the step number 1. So in step number 1, first we will calculate the transition voltage. Here, now the question arises, what exactly the transition voltage is. So the transition voltage is the voltage at which diode changes its behavior. Diode changes its behavior means what? It means if the diode is forward biased, then at transition voltage, it will be reverse biased and vice versa. So in short, transition voltage is the voltage at which diode will change its behavior. Now the question arises, how do we calculate the value of transition voltage? So the magnitude of transition voltage is equal to the battery voltage. So here we can see the battery voltage is 5 volts. Therefore, I have taken the transition voltage also equal to 5 volts. Now, here we need to see whether this transition voltage will be positive or negative. So how do we come to know? So for this, in any numerical of parallel clipper, the battery will be connected in two ways. If the battery is connected in this way, means positive plate comes first, and if it is having voltage V, so it will be plus voltage. And if the battery is connected in this way, the voltage will be negative. So in any numerical of parallel clipper, battery will be connected either this way or this way. So because the positive terminal of the battery comes first, so we will take this 5 volt as positive 5 volts. So this is how we can calculate the transition voltage. Now we need to draw this transition voltage in the input waveform. So here you can see this red dotted line is of transition voltage. This is the transition voltage. So here we can see the transition voltage cuts the input waveform or positive half cycle of the input waveform at two places, this point and at this point. So this transition voltage divides the positive half cycle into three parts: 0 to 1, this is first part; 1 to 2, this is second part; and 2 to 3, this is third part. Okay. Now, in step number 2, we will find V naught during positive half cycle. So, during positive half cycle, this will be plus and this will be minus. And V naught is always calculated between plus and minus. Okay. Because positive half cycle is divided into three parts, therefore I have taken three cases. Case number 1, case number 2, and case number 3. So let's see what exactly these three cases are. So the first case is Vi is less than 5 volts. Why is it so? Because in the input waveform, you can see this input is below this transition voltage line. Means transition voltage is greater than the input voltage. And the same I have written in case number 1. Vi less than 5 volts. Okay. Now let's take the case number 2. In case number 2, you can see the input voltage exceeds the 5 volt, which is the transition voltage. That means in case number 2, input is greater than this 5 volt, which is a transition voltage. So in case number 2, I have written Vi is greater than 5 volts. Case number 3 correspond to the portion between point number 2 and point number 3. So in case number 3, again you can see the input voltage goes below the 5 volt line or transition voltage. That means Vi is less than 5 volts. Okay. So these are the three cases during positive half cycle. Now let's take all three cases one by one. So case number 1, when Vi is less than 5 volts. Now we need to check whether diode is forward biased or reverse biased. So in the given circuit, you can see there are two voltages, input voltage and battery voltage. So whichever is higher, that will decide whether diode will be forward biased or reverse biased. So in case number 1, you can see 5 volt is greater than Vi. That means this battery voltage is going to decide whether diode is forward biased or reverse biased. So you can see positive terminal of the battery is connected to the negative terminal of the diode. Therefore, this battery voltage is going to turn off this diode. That means diode will be reverse biased. One second. Diode will be reverse biased. Sorry, I have written it by mistake. Let me correct it. So during case number 1, 5 volt is greater than Vi. So here we can say the positive terminal of the battery is connected to the negative terminal of the diode. Therefore, diode will be reverse biased. Diode will be reverse biased. And when the diode is reverse biased, it will behave like open circuit. It will behave like open circuit. So the circuit will be like this. So therefore, V naught will be equal to the Vi. So we can write V naught will be equal to Vi. It means whatever the input voltage is, the same we will get at the output. So let's see what is the input voltage during case number 1. So during case number 1, if we see the input waveform, so during case number 1, input starts from 0 and it goes at point 1. So the output will be similar to the input voltage. So it will start from 0 and it will go up to 5 volts. Okay, so V naught is equal to Vi. This is the output during case number 1. It means whatever the input is, the same we will get at the output. So the output is just similar to the input voltage during case number 1. Now let's take case number 2. Case number 2, we can see Vi is greater than 5 volts. Let me connect the diode. So case number 2, Vi is greater than 5 volts. Now here, Vi is going to decide whether diode will be forward biased or reverse biased. So the positive terminal of Vi is connected to the positive terminal of diode. That means diode will be forward biased. Diode will be forward biased. And when the diode is forward biased, it will behave like short circuit. It will behave like short circuit. So the circuit will be like this. So in this case, V naught will be equal to the voltage across RL, and the same voltage will be across this branch which I have mentioned, A and B. So the V naught will be equal to the voltage between point A and B, and which is equal to plus 5 volts. So during case number 2, the output will be plus 5 volts. So this is how we can calculate the output voltage during case number 2. Now let's mark it on the output waveform. V naught is equal to 5 volts. So these two lines correspond to case number 2, where I have to mark the output voltage. The output is constant 5 volts. Okay, so this is the output correspond to case number 2. Now let's take the case number 3. So case number 3 and case number 1 are similar. Vi less than 5 volts. So here also diode will be reverse biased. And when the diode is reverse biased, it will behave like open circuit. And in this case, V naught will be equal to Vi. Similar to the case number 1. So in case number 3 also, whatever the input is during case number 3, the same we will get at the output. So let's see how is the input during case number 3. So if you see the input waveform, case number 3 correspond to the portion between point 2 and point 3. So input starts from point number 2 and ends at point number 3. Or in other words, during case number 3, the input starts from 5 and ends at 0 volts. So similarly, the output will be like this. It will start from 5 volt and will end at 0 volt. So this is the output correspond to case number 3. So this is how we can calculate the V naught during complete positive half cycle. Now let's take the step number 3. In step number 3, we are going to calculate V naught during negative half cycle. So this shaded portion is the negative half cycle. So while calculating the V naught during negative half cycle, in the given circuit, we will change the polarity. During negative half cycle, this is minus and this is plus. And here I will connect the diode. So diode is like this, which is given in the given circuit. So here also, we will see whether the diode is forward biased or reverse biased. So first start with the input voltage. So the negative terminal of input is connected to the positive terminal of the diode. So input voltage will make the diode reverse biased. Now let's check with the battery voltage. the positive terminal of the battery is connected to the negative terminal of the diode. So this battery voltage also makes the diode reverse biased. So both the input voltage as well as battery voltage, both are making the diode reverse biased. And if the diode is reverse biased, the diode will behave like open circuit. The diode will behave like open circuit. And now we need to find the V naught. So the voltage V naught will be equal to the voltage across RL branch, and the same will be equal to input voltage. So V naught will be equal to VIA. So V naught will be equal to VI. That means during negative half cycle, whatever the input is, the same will be equal to output voltage, both in magnitude as well as in shape. So let's see. So this shaded portion is the input voltage during negative half cycle. So the same will be output during negative half cycle. This is minus 10 volts. So this is the complete output of the given circuit. So this is an example of parallel bias clipper, and in this numerical we have taken an ideal diode. Now let's do another problem in which we will take the practical diode. So this is problem number 2. The given circuit, you can see in this we have taken the practical diode, and that the diode is of silicon type. Okay. Here the input is triangular instead of sinusoidal. So first of all, we will draw the input waveform. So here you can see we have drawn the input waveform, which is triangular, and it is having the magnitude of plus 10 volt during positive half cycle, and it is having the magnitude of minus 10 volt during negative half cycle. So again, let's start with the step number 1. So I have told you earlier, first we need to calculate the transition voltage. So here the transition voltage will be equal to the battery voltage. So here the battery voltage is 5 volts. So I have taken 5 volts here while calculating the transition voltage. Now, this is a practical diode, silicon diode. And as we all know, the voltage drop across silicon diode is 0.7 volt. So if I replace this diode by a battery, it means we need to replace this diode by a battery which is having a magnitude of 0.7 volt. So the battery will be connected like this. And this is a given battery. So the circuit will be like this. So the circuit will comprise of 2 batteries. This is a battery voltage 5 volts, and this is a voltage drop across silicon which is of 0.7. So if I need to calculate the transition voltage, these 2 voltage will be considered. So first, if I take the voltage across silicon 0.7, so here I have taken 0.7, but this is with the negative sign. Why I have taken negative sign? Because in the first numerical, I have told in any numerical of parallel clipper, if the battery is connected like this, the voltage will be negative. And if the battery is connected like this, the voltage will be positive. So this 0.7 will be negative and this 5 volt will be positive. So total transition voltage comes out 4.3 volts. So this is how we can calculate the transition voltage in case of practical diode. Now we need to draw this transition voltage in the input waveform. So here you can see this red dotted line is the transition voltage, which is having magnitude of 4.3 volts. Let me change the color of the pen. Okay. So here we can see the transition voltage cuts the input waveform at 2 points, this point and at this point. Or in other words, we can say the transition voltage or the positive half cycle is divided into 3 parts. 0 to 1, this is first part. 1 to 2, this is second part. and 2 to 3, this is third part. So this transition voltage divides the input waveform or positive half cycle of the input waveform in three parts: 0 to 1, 1 to 2, and 2 to 3. Now in step number 2, we will calculate the output voltage during positive half cycle. So while calculating the V0 during positive half cycle, this will be plus and this will be minus. And output is always taken between plus and minus. So here we can see during positive half cycle, we have taken three cases: case 1, case 2, and case 3. As just we took these three cases in the first numerical. So case number 1 correspond to the portion between point 0 and 1. Case number 2 correspond to the portion between point 1 and 2. And case number 3 correspond to the portion between point 2 and 3. So these two lines correspond to case number 1. These two lines correspond to case number 2, and these two lines correspond to case number 3. So let's take case number 1 first. So in case number 1, you can see I have written Vi is less than 4.3, which is a transition voltage. So as I have told you earlier, whichever is higher, that voltage is going to decide whether diode will be forward biased or reverse biased. So this battery voltage is greater than input voltage. That means this battery voltage is going to decide whether diode will be forward biased or reverse biased. So here we can see the positive terminal of battery is connected to the positive terminal of silicon diode. That means silicon diode will be forward biased, and the same I have written here. And when the diode is forward biased, it will behave like short circuit. So the circuit will be like this. It will behave like short circuit. So in this case, V0 will be equal to the voltage across RL branch, and the same will be equal to the voltage between point number 1 and point number 2. So the voltage between point number 1 and 2 is plus 5 volts, which is the transition voltage. So I have written here, sorry, I will have to take the voltage across silicon diode also. So that will be like this. This is 0.7. So the voltage between point number 1 and 2 will be minus 0.7 and plus 5. So that comes out 4.3 volts, which is equal to the transition voltage. So case number 1, V0 will be equal to the voltage equal to transition voltage 4.3. So let's mark it on the output waveform. So during positive half cycle, output voltage is plus 4.3. So let's mark it. This is 4.3. So this is constant 4.3 volts. Okay. Now let's come to the case number 2. So in case number 2, Vi is greater than 4.3 volts. So this Vi is greater than. So again, I need to put the diode. Sorry, diode is connected in this way. So case number 2, Vi is greater than the battery voltage or transition voltage. So here the positive terminal of battery input voltage is connected to the negative terminal of the diode. Therefore, diode will be reverse biased. And the same I have written in case number 2. And if the diode is reverse biased, it will behave like open circuit. It will behave like open circuit. So in this case, V0 will be equal to Vi. So the same I have written in case number 2. V0 is equal to Vi. So whatever the input voltage is during case number 2, the same will be the output voltage, both in shape and magnitude. So in case number 2, V0 will be equal to Vi. So let's see how the input voltage is during case number 2. So in case number 2, the input starts from 4.3 and it is going up to 10 volts and again returning back at 4.3. So the same will be the output. It will start from 4.3. If it is 10 volts, so it will go up to 10 volts and will return back at 4.3. So this is the output during case number 2. Now let's take case number 3. In case number 3 and case number 1 are similar. So here in case number 3, diode will be forward biased as we discussed in case number 3. And when the diode is forward biased, we will get V naught is equal to 4.3 volts, which is equal to the transition voltage. So these two lines correspond to case number 3, in which I need to draw the output voltage equal to 4.3 volts. So this will be the output during case number 3, which is equal to 4.3 volts. So this is the complete output during positive half cycle. Now let's come to the output during negative half cycle, which is the shaded portion. So while calculating output during negative half cycle, first we need to change the polarity. So this during negative half cycle, this will be minus and this will be plus, but the output voltage polarity won't get changed. So now during negative half cycle, let's check with the input voltage first. So the negative terminal of input voltage is connected to the negative terminal of the diode. Therefore, diode will be forward biased. Now let's check it out with the battery voltage. So the positive terminal of the battery is connected to the positive terminal of the diode. That means this will make the diode forward biased. Hence, we can see both input voltage as well as battery voltage are going to make the diode forward biased. So the same I have written in step number 3. In step number 3, the diode will be forward biased. And if the diode is forward biased, it will behave like short circuit. It will behave like short circuit. Here the battery voltage, the voltage across silicon diode will be like this, 0.7. So now we need to calculate the V naught. So V naught will be equal to the voltage across this branch between point A and point B. And the voltage between point A and B will be equal to minus 0.7 and plus 5. That comes out the transition voltage, which is equal to 4.3. So during negative half cycle, the output voltage is 4.3 volts. So we need to draw this output voltage. So during negative half cycle, during complete negative half cycle, the output voltage is plus 4.3 volts. So this will be the output voltage. So this is the output during negative half cycle. So this is how we can calculate the output voltage of the given circuit, or we can draw or sketch the output voltage of the given parallel biased clipper with the practical diode. So this is all about the series parallel biased clipper. These are the references. Thank you.